In this video, we discuss preliminary theory for higher order ODEs. In particular, we're going to discuss the existence and uniqueness theorem for IVPs and the difference between IVPs and BVPs, excuse me. So here is an nth order linear ODE. We know it's linear because y and y's derivatives are all raised to the first power, or possibly they don't appear in the equation at all. The coefficient functions, a sub n of x, a sub n minus 1 of x, a sub 1 of x, and so on, all of those depend only on the independent variable. In this case, it's being labeled as x, and the function on the right-hand side depends only on x. So this is a linear nth order ODE, and we've got n initial conditions associated with it. So sorry about that. Sorry, my technology has been a little buggy lately. I don't understand why it cuts out the way it does. At x equals x naught, y is equal to y naught. At x equals x naught, y prime is equal to y1. And all of this is given to us. At x equals x naught, y double prime is equal to y2. And at x equals x naught, y sub n minus 1 is evaluated at, and it's given by this value. So these are given numbers. X naught is known. It's going to be given to you. And y sub 0 through y sub n minus 1 are numbers as well. So these are n initial conditions. You've got n minus 1 of them right here and 1 of them here. Together, these initial conditions in this differential equation form what's called an initial value problem. Generally, the nth order ordinary linear differential equation is going to have n, well, we'll talk about the linearly independent solutions in a bit, but you're going to have n arbitrary constants in your general solution. In order to find the values of those n arbitrary constants, you're going to use these n initial conditions. Now let's talk about existence and uniqueness for the solution of this IVP. If those coefficient functions, so the a sub n of x, a sub n minus 1 of x, the functions in front of y and y's derivatives on the left-hand side, and the function on the right-hand side are continuous on an interval I, and the leading coefficient function, which is denoted by a sub n of x, if that function is non-zero on the interval I, and x equals x naught, that's the x value that's given to us in our initial conditions, is on the interval I, then we're guaranteed that a solution of the IVP exists and it's unique. So we might be asked to determine the largest interval on which the conditions of the theorem are satisfied. So in other words, where's the largest interval that we can expect to find a unique solution to this initial value problem? Well, first of all, I notice that it's a second order differential equation, and I'll label this a sub 2 of t. This is a sub 1 of t, this is a naught of t, and this function on the right-hand side is g of t. And we're given y of 0 equals 0 and y prime of 0 equals 1. Notice that we're using t as the independent variable instead of x. That's totally fine. Now, in order to determine the largest interval where the conditions of the theorem are satisfied, I need to think about the coefficient functions and that g of t on the right-hand side, and I need to think about where they're continuous. Well, this is a quadratic function. It's continuous all the time, so we're fine there. This is a linear function. It's actually a really simple linear function. It's just a horizontal line, y equals 1. So that's continuous. That's a linear function that's continuous, and that's y equals 0, the 0 function. It's continuous all the time. So all of these guys are continuous for all real numbers, so those are not going to cause any restrictions on that interval I that we're interested in. But in order to find that interval I, we also need that leading coefficient function to be non-zero. So in our case, n is equal to 2 because that's the highest order derivative in our differential equation. So the coefficient in front of that is denoted a sub 2 of t. So notice here that we've got subscripts on each of these functions. The subscript agrees with the order of the derivative. So if this is the second derivative, that's a sub 2. If it's the first derivative, that's a sub 1. If it's y, which is the 0th derivative, we call that a sub 0. So when they say this, what they're saying is the leading coefficient function, the coefficient of the nth derivative of your dependent variable with respect to your independent variable, that can't be 0 on the interval that you're looking for. So in our case, a sub 2 of t cannot be 0. So we take that a sub 2, we factor it, and we set that equal to 0. The only way this product is 0 is if this equals 0 or if this equals 0. So we're going to have a problem at t equals 2 and t equals 1. Because at t equals 2 and t equals 1, this would be 0, and that's not allowed. So actually, maybe I should say this is not equal. Well, actually, those are equal to each other, but that is not equal to 0. And if this is not equal to 0, this is not equal to 0, and that is not equal to 0, or we're saying that t cannot be 0, or excuse me, t cannot be 2, and t cannot be 1. So when we're talking about our largest interval of existence, the largest interval where that unique solution exists, it's going to be one of these intervals. T equals 1 and t equals 2 are here and here on the number line. And so these separate the number line from negative infinity to infinity into 3 intervals. You've got the interval from negative infinity to 1, the interval from 1 to 2, and the interval from 2 to infinity. Now, when you're trying to decide between these 3, this last condition is really important. The initial value of your independent variable needs to be on the interval. It needs to be in the interval that we're talking about. So I go to my initial conditions and I see that y of 0 is equal to 0 and y prime of 0 is equal to 1. So this is our t naught. T naught is equal to 0. So I need an interval that does not include t equals 1 or t equals 2, that includes t equals t naught, and this is the one that includes t equals 0, the one from negative infinity to 1. So that's our answer, but I wouldn't write it this way. This is my scratch work. It's important scratch work, but I need to state my conclusion more clearly. So basically what I do when I want to state my conclusion is I go through each of these 3 conditions for the existence and uniqueness theorem. I say, since the coefficient functions and g of t, which happen to be 0, are continuous on negative infinity to infinity, that's the entire real line, and our leading coefficient function is non-zero on the interval from negative infinity to 1, and t naught equals 0 is in the interval from negative infinity to 1, then I equals the interval from negative infinity to 1 is the largest interval on which the IVP has a unique solution. So you're just checking continuity, you're checking to make sure that leading coefficient is non-zero, and then you're picking from those 3 intervals the one that includes your initial condition. Okay, so let's do another example. So here's our second example. We've got 5 times the 4th derivative of y minus 3 times the 3rd derivative of y plus 2 times the 2nd derivative minus 1 times y is equal to 0. And we're given that y of 0, y prime of 0, y double prime of 0, and y triple prime of 0 are all 0. Well, in order to find the largest interval on which we have a unique solution to this IVP, we need to look at the continuity of the coefficient functions. So our first coefficient function is 5, then we've got -3, then a 2, and then a 1. Those are just constant functions. They're continuous for all real numbers. And then look at the function on the right-hand side, 0. It's also continuous for all real numbers. So those guys are continuous. And then we also have to think about whether that leading coefficient function is equal to 0. Well, if the leading coefficient function, which since it's the coefficient of the 4th derivative, we'll call that a sub 4 of t, since that's equal to 5, well, we know that that's never equal to 0. 5 is never equal to 0 for any value of t. Since that's true, and t naught, which is 0, is a real number, all 3 of the conditions are satisfied for all real numbers. These guys are continuous. This leading coefficient is 5, it's never 0, and t naught equals 0 is on the interval of real numbers. So the largest interval I, for which a unique solution to this IVP exists, is the 0 function, or excuse me, not the 0 function, is negative infinity to infinity. Now, when we talk about the solution to this, I was getting ahead of myself. I was thinking about this next part. Sorry. You might be able to guess what that unique solution to the IVP is. You're asking yourself, what function can you plug in 0, and the function itself, the first, second, third, and 3rd derivative are all equal to 0 at t equals 0. And that function also satisfies this equation, Well, it turns out that the solution of this is y of the independent variable, let's just assume it's x, is equal to 0. Well, I guess we said it was t here, so I'll say y of t is equal to 0 for all real numbers t. That's called the trivial solution. It's the 0 solution. And most of the time when we're looking for a solution to a differential equation, we're not looking for the trivial solution. But if I take the fourth derivative of 0, I get 0. And if I take the third derivative of 0, I get 0. Same is true of the second derivative in the function itself. So if I plug y equals 0 into this, I do get 0. So y equals 0 satisfies the differential equation. And of course, y of 0, y prime of 0, y double prime, and y triple prime of the 0 function are all going to be equal to 0. So you might think, okay, if this is the solution that I found, it's probably not the solution that I'm looking for because it's the trivial solution. And most of the time you would be right if it wasn't an IVP. But this is an IVP. We're not only given the differential equation, but we're also told this. Since this function satisfies this differential equation and all of these initial conditions, and the theorem says that we're guaranteed a unique solution for all real numbers. Once you find that solution, which happens to be the trivial solution, you found it. That's the unique solution. There's no other solution out there to this differential equation subject to these initial conditions. So that's what the theorem is telling us, that we have a unique solution, and if it happens to be the trivial solution, that one's it. Now let's look at this example. It's a second order differential equation, and that means this first coefficient function can be denoted by a sub 2 of t. The function in front of y prime, that's just an implied 1, that's what we'll call a sub 1 of t. Now there's no y term here, so a sub 0 of t, the coefficient of y is just 0 because there's no y. And the function on the right-hand side is g of t, which happens to be 0. Now sine of t, 1, 0, and 0, those are going to be continuous for all real numbers. So that first condition where we're looking at the coefficient functions and we're thinking about whether they're continuous, that's satisfied for all real numbers, and it's not going to affect our interval of existence at all. So we don't have to worry about that. But we do have to worry about this leading coefficient function being 0. So let's look at the sine function. Remember how that works. The sine function looks like this, and it repeats every 2 pi. And it goes on forever in both directions. So this is the t-axis, and that's the y-axis, and this is y equals sine of t. We're going to have a problem here whenever sine of t is equal to 0, because our largest interval of existence can't allow that leading coefficient function to be 0. So our leading coefficient function is 0 at all of the points where this sine of t function crosses the t-axis. So 0 and pi and 2 pi and 3 pi and 4 pi and negative 2 pi and so on. All of those are t values where this is equal to 0. So those t values are going to restrict that interval of existence that we're looking at. So when I'm looking at the entire real line and I'm thinking about all the possibilities for my interval of existence, I might look at it like this. And you have to remember that the pattern continues. But our interval of existence could be this one, or this interval, or this interval, or this interval, or the one after that, and so on. You're going to see this pattern continuing, because a sub 2 of t, sine of t, that's going to equal to 0. That equals 0 when t is any multiple of pi, 0 pi, 1 pi, 2 pi, 3 pi, 4 pi. So if t is n times pi, where n is an integer, then the leading coefficient function is 0, and we don't want that. So our interval of existence has to be one of these types of intervals. Now you have to pick when you're trying to decide what your interval of existence is for the particular initial value problem. You have to choose among these intervals. You've got to choose the one that includes that initial value of your independent variable. So in this case, our initial value is 3 pi over 2. That's 1.5 times pi. 3 pi over 2 would be right here. So the interval that we're looking for is this interval. So it's the interval that starts at pi and ends at 2 pi. But the reasoning is this. The coefficient functions are continuous for the entire real line. A sub 2 of t is not equal to 0 on this interval from 0 to 2 pi, or from pi to 2 pi, excuse me, and the initial value of t naught is on that interval. So to justify our answer, we'll say this. We'll say since the coefficient functions and g of t, as a function on the right-hand side, are continuous for all real numbers, and a sub 2 of t is not equal to 0 on the interval that we're interested in, on that interval from pi to 2 pi, and the interval from pi to 2 pi includes that 3 pi over 2, that interval from pi to 2 pi is the largest interval on which the initial value or the conditions of the theorem are satisfied. Or in other words, this is the largest interval where we're guaranteed to have a unique solution. That's what the theorem is about. It's about whether a solution exists and whether it's unique. So that's the first part of this video. Now we'll talk about boundary value problems. We talked about these briefly at the very beginning of the semester. A boundary value problem is very similar to an initial value problem. Here's the difference though. In a boundary value problem, the dependent variable and its derivatives are given at more than one value. Oops, I forgot to write one. More than one value of that independent variable. So here, all of these, y prime, y double prime, all the way up to the n-1th derivative, they're all given at x equals x naught. With a boundary value problem, you might have some given at x naught and some given at x sub 1. You might even have linear combinations of those. But let's look at a simple BVP. We've got x double prime plus 16, x equals 0. And we've got x of 0 equals 0 and x of pi over 2 equals 0. Now on the surface, you might think this is an IVP, but notice the dependent variable is t. And here we're given x at t equals 0 is 0 and x at t equals pi over 2 equals 0. Since I've got two of those, that makes this a boundary value problem. We call these guys boundary conditions or BCs. Now, there are a lot of boundary value problems, especially when you study partial differential equations, but the theory is not as nice as it is for the initial value problems that we study in our class. We're not guaranteed a unique solution to this boundary value problem. We might get one solution, or we might have infinitely many solutions, or we might have no solution. Just to show you, I'm going to state the solution to this differential equation. We're going to solve this differential equation later in the semester, but I'll just state it for you and then show you what happens when we use these initial conditions. So this is our first example for this boundary value problem. It turns out that the general solution of this differential equation is x of t equals a constant times sine of 4t plus a constant times cosine of 4t. That turns out to be true. And if I take the second derivative of this and I plug it in, it turns out that I'll have a negative 16 c1 sine of 4t plus negative 16 c2 cosine of 4t plus 16 times all of this. And the 16s cancel, you know, the terms cancel and you get a 0. So this works. It's the general solution. It's the family of solutions that contains all solutions. And we'll learn how to find this later this semester. Let me just make that note for you. Now, if I have boundary value conditions, those boundary value conditions may be able to tell me the values of C1 and C2, but they may not. So let's look at what happens. If I know that x equals 0 and t equals 0, I can use that possibly to find the value of C1 or C2. Because x of 0 equals 0 means that when t equals 0, x equals 0. So we can replace t with 0. And see what we get. Well, sine of 0 is known to be 0. So that guy's gone. And cosine of 0, we know that's 1. So x of 0 equals 0 times c1, which is 0, plus 1 times c2, which is c2. And we'll set that equal to the given value of x. We're told that when t equals 0, x equals 0. So we'll set that equal to 0. And this first condition tells us that c2 must be 0. Okay, so we know that. So using that now, we can say that our solution must have this form. X of t equals c1 times sine of 4t plus 0 times cosine of 4t. So x of t is a constant times sine of 4t. Okay, now let's use the second boundary condition to try to find the value of c1 if we can. You treat this almost the same way that you treat an initial value problem. But when you're given boundary values, you don't necessarily get C1 and C2 every time. So this boundary condition tells us that when t equals pi over 2, x is equal to 0. So I've got x of t equals C1 times sine of 4 times t. I just replace t with pi over 2. So this is sine of 2 pi, and sine of 2 pi is 0. And that's equal to 0 regardless of what C1 is. And normally we would set that equal to 0 and solve for C1, but 0 is already equal to 0. So actually, it does not matter what C1 is. That second condition is satisfied. So that means the solution to the boundary value problem is C1 times sine of 4t. Because this function satisfies the differential equation. If we take the second derivative, we add 16 times the original function, we get 0. And when t equals 0, x equals 0. Because we'll have x of 0 equals c1 times sine of 0 is 0. And when t equals pi over 2, we get c1 times sine of 2 pi, sine of 2 pi is 0, so we get x of pi over 2 equals 0. So we actually have infinitely many solutions. Now I know it looks like you only have one solution, but there are infinitely many solutions there because that C1 can take on any value. Sine of 4t works. Negative 100 times sine of 4t works. 0 works. 5 times sine of 4t works. Any real number C1 that you choose will work. This is a solution to the initial or to the boundary value problem. Now, if I take the same differential equation, but I change these guys a little bit. So I've got x of 2 or excuse me, the differential equation is x double prime of t plus 16x of t equals 0. And we still have x of 0 equals 0 and x of pi over 2 equals something else this time. Let's say that it equals 1. Well, in this case, what I end up with is this. X of 0 equals 0. We already know because of what we did in the last example. When you take x of 0 and you simplify it and you set that equal to 0, it turns out that C2 must be 0. So x of 0 equals 0 implies that C2 is 0. And this is where our general solution that we're considering is C1 sine of 4t plus C2 cosine of 4t. So this implies that C2 equals 0, and that implies that at this point, without looking at any other conditions, x of t must be a constant times sine of 4t. Now we'd like to find the value of that constant, but we also know what happened when we plugged in pi over 2. When we evaluate this function at pi over 2, remember what we got? We got 0. This is sine of 2 pi, and sine of 2 pi is 0. And so we have x of pi over 2 is equal to 0. And we're setting that equal to what they gave us. We set that equal to 1. Well, 0 is never equal to 1. This is never true. It does not matter what C1 is, 0 will never equal 1. So this boundary value problem has no solution. Because it's not possible for the differential equation and this boundary condition to be satisfied at the same time. So you could have infinitely many solutions, or you could have no solution, or it's possible that you could have one solution. Let's look at this last one. You might have x double prime plus 16x equals 0, x of 0 equals 0. And then rather than giving you x at pi over 2 equals 0, maybe they tell you x prime at pi over 2 equals 0. Well, the first condition, if we are treating this general solution, x of t, as C1 times sine of 4t plus C2 times cosine of 4t. If that is our general solution, x of 0 equals 0 implies that C2 equals 0, and that means that x of t is just some constant times sine of 4t. So we're there already. Now, in order to find the value of that constant, we can try to use this second initial condition. And maybe that will get us a value for c, maybe it won't. We'll see. So in order to do that, I need to take the derivative of this. The derivative of sine of 4t is cosine of 4t times the derivative of the inside, which is 4. So you're computing that first derivative. Then you want to evaluate at t equals pi over 2. And this is cosine of 2 pi over here. And cosine of 2 pi is equal to 1. So we get 4 times C1 times 1 must be 0. Actually, let's use a different initial condition. Let's use 1, just to make it more interesting. So I've got x prime of pi over 2 is equal to 4 times C sub 1, and that value has to be 1. We're setting that equal to 1. So we'll solve for C1. So C1 must be 1/4. And that means our solution, x of t, is C1, which is 1/4, times sine of 4t. So we evaluated at t equals pi over 2, and then we set x at pi over 2 equal to the given value. We could have made it 0, but I didn't like that one because it was just going to give me the 0 solution, so I tried to make it more interesting. So we set this equal to whatever that given value is, and I changed the example and I made that a 1. And then we solve for c sub 1. And then once you do that, you back substitute. So this is your answer, and that's one answer. So this boundary value problem has one solution. I was writing one solution and then thinking single solution, so sorry about that. So a boundary value problem can have a single solution or infinitely many solutions or no solutions. And it's not that easy to tell the difference when you're looking at this boundary value problem versus this boundary value problem versus this boundary value problem that we started with. They look sort of typical, harmless. They don't look that exciting or impressive at all. They don't look that different from the initial value problems, but they're very different. With initial value problems, we have this beautiful existence and uniqueness theorem that tells us if the coefficient functions and the function on the right-hand side are continuous, and the leading coefficient is non-zero on an interval, and the value of the independent variable given in the initial conditions is on that interval, you're guaranteed a solution exists and it's unique and that's the one, and you're just going to find it by usually finding the initial or finding the general solution, excuse me, and then using these initial conditions to find the values of the arbitrary constant. But it's not so obvious, it's not so clear with boundary value problems. It looks like it's harmless. It looks like it's not that difficult. And it isn't really that difficult as we've seen, but there are no guarantees that you have a unique solution like we have with those guarantees for initial value problems. Now, for the most part in this course, we're going to focus on initial value problems and not boundary value problems. You're going to see boundary value problems more if you take partial differential equations.